Welcome to another podcast. In this episode, we're going to be taking a look at another repeated roots example for eigenvalue method. If you recall, in the previous video, we actually were able to find a full set of eigenvectors for our repeated root. That is not always the case, as this video will demonstrate. So I want to start by looking at the system. So let's let xy be equal to coefficient matrix. So here our matrix A is given by this 2 by 2 matrix. Let's go ahead and calculate the characteristic equation here. So this is the determinant of this matrix. So lambda squared minus the trace is -2 plus -2 is -4. So it's minus the trace, that's why it's plus 4. And then plus the determinant here is 4 minus 0. So you can see clearly here that this has a repeated root. And so my eigenvalues are both -2. So case 1 is, alright, let's use lambda 1 equal to -2, and I'd be looking for a solution of the form alpha 1 e to the -2t. Alright, so I'm looking at a minus -2i, so this would be a minus -2i times alpha 1 equal to 0, or this is the same thing as a plus 2i. So what I'm going to be doing is I'm going to actually be adding 2, because this is a negative eigenvalue, I'm going to be adding 2 to all of the diagonal elements. And so if you take the matrix A and you add 2 to those elements, you get 0, 0, 0, and 1. And so you've got A1 and A2, and we need to set this equal to the 0 vector. So what are the values of A1 and A2 that would work here? Well, I think you can see, if you study this close enough, I think you can see that A1 would be 1, and then A2 could be 0. So I've got alpha 1 is 1, 0, and so my solution x1 is 1, 0, e to the -2t. Alright, so case 2 is you would have, let's see here, lambda 2 would also be -2, and the question is, can I find an alpha 2? Well, the answer here is no. If you look at A1 and A2 in the above, it doesn't matter what I pick. The only thing that would work would be a constant multiple of this. So I could pick anything. So A1 could be, this could be anything. But in order for this to be 0, this second thing is going to have to be 0. So anything I get is going to be a constant multiple of the eigenvector 1, 0 that I already have. So this is out. I can't look for an x2 of that form. And so sort of a revised case 2 would be, okay, what did we do back when we had repeated roots? Well, when we had a repeated root, the idea was that we looked for a solution that's a little bit different. So I'm going to look for a solution here of this form. I'm going to look for one that is a vector times e to the lambda t, which is not going to be enough because we already said that's not enough. So what we did back in the first part of class, or the first part of the semester, was, okay, well, I'm going to also look for t e to the lambda t. So that's what we're going to do here. We're going to look for a solution of the form e to the lambda t plus another one times t e to the lambda t. So the question is, what would that look like? So if I plugged x2, so I'm going to plug x2 or substitute x2 into our system, then what that ends up looking like is, okay, so this is the vector x. If I look at x prime and plug it into it, then it's going to be I'm going to take each of these pieces and I'm going to take their derivative, okay? So the derivative of this piece, so that this is the derivative, so the way to look at this is x2 prime. What is x2 prime? Well, x2 prime is equal to, we would get a lambda term to come out here, so lambda alpha naught e to the lambda t, plus, and you can see here that because of this t here, I'm going to have to do product rule. So if I want to find the derivative of this, product rule would say, okay, let's go ahead and take the alpha 1 part. So the derivative of t is 1, so it would be alpha 1 e to the lambda t. And then the second part would be, if I take the derivative of e to the lambda t, would be lambda alpha 1 t e to the lambda t. So that would be x2 prime. Then I need to know what is a times x2. Because these two have to match, right? If I'm going to plug x2 into this equation, then x2 prime has to match ax2. And so if I apply the matrix A to the vector x2, then that's A applied to the vector alpha naught, e to the lambda t, plus A applied to the vector alpha 1, t, e to the lambda t. So what you see here is things have to match up. For starters, if you look at this, here I have the coefficient of e to the lambda t as being what? Well, you can see here that in each of these pieces, if I look here and here, those are the coefficients of t. So the t e to the lambda t term, those two terms have to match up. Well, that says that a alpha 1 has to equal lambda alpha 1. Well, that just says that lambda and alpha are eigenvalues. So lambda and alpha 1 have to be an eigenvalue eigenvector pair, which that's what we did. Right? So we already have that one. So the alpha 1 that we need is already right here. We've already done that. So corresponding to lambda equal to 2, we have the eigenvector 1, 0. All right, the other piece of this is if I want to solve for alpha 0, the other eigenvector here, then I look at the e to the lambda 2 and I say, okay, a alpha 0 has to be the coefficient of e lambda t. So where is e to the lambda t? There and there. Well, that says that lambda alpha 0 plus alpha 1 has to be equal to a alpha 0. And if I do a little bit of rearranging here, then I can write this as a minus lambda I alpha 0 equals alpha 1. And so two very important equations here. How to find this, and then how to find this. So if you run into a situation where you cannot find two linearly independent eigenvectors for a repeated root like we couldn't here, then the way to find the second one is using this formula. So I need to find alpha naught using this. So alpha naught is what's referred to as a defective. So this is the eigenvalue, excuse me, is referred to as being defective. So this eigenvalue here, because I couldn't find a complete set, so this eigenvalue is called a defective eigenvalue. And in order to find a complete set, I have to generate a second one, and the one that we're generating here is called a generalized eigenvector. And so that's what I'm finding using this formula is a generalized eigenvector. Because what I'm looking for is I'm looking for an eigenvector that points in the same direction as the one I already have. And I'm having to create it. Now, the way to do this then is via this formula, I look at the matrix A minus lambda I, which is A plus 2I, which we've already done. So that matrix is the same as this one over here. It's 0, 1, 0, 0. Then I have to multiply it times an A naught. So let's let the components of that be B1 and B2, since they wouldn't be the same components as the A1 and A2 over here. And that has to equal alpha 1, which is the eigenvector we've already found. So if we set it equal to the eigenvector we've already found, then what you see here is you're gonna run into a little bit more problems with this one in terms of trying to find it. And so what you end up having in this case would be, let's see, a b1 equals to 0 and b2 equals 1. So you can see that would, if you had b1 is 0, b2 is 1, you would still get a 1 in the top row and you would still end up with zeros in the bottom. And so what we found is that this generalized eigenvector is 0, 1, and you can see now that the generalized eigenvector and the original eigenvector, those are linearly independent. Now, the question is, what does the solution look like? And so this is what drives students nuts on this problem, is they can usually do the work I'm showing here, but then they have problems coming up with the solution. So what is the solution in this case? Well, all you have to do is simply look back at the pieces that we have constructed. So if I want to find the solution x, that's equal to c1 x1 plus c2 x2. So x1, we already know it's alpha 1 e to the negative 2t, so it's 1, 0 e to the negative 2t. And then what is x2? Well, here's where you have to be careful. Our form of x2, you can see here, was this. So this is our x2. So it's going to be of the form alpha naught plus alpha 1t e to the lambda t. So alpha naught is 0, 1 plus alpha 1 is 1, 0 times t e to the lambda, but lambda is negative 2, e to the negative 2t. So the form of the solution is c1 alpha 1 plus c2 alpha naught plus alpha 1 t e to the negative 2t in this case. So the way that you would probably want to go about writing this is just c1 1, 0 e to the negative 2t plus c2, combine this. So if you read the top component of this vector, it's 0 plus 1 times t. So the top component of the vector is t, and the bottom component is 1. 1 plus 0 times t. And so this would be my solution in this case. And this matches our experience from earlier in the semester. When you have a repeated root, usually you have to involve t times the exponential in order to find the other linearly independent solution. And it's the same idea here when you have a defective eigenvalue. Finding the defective if you have a defective eigenvalue, finding the generalized eigenvector corresponds to this process that I did right here. So this is how you find the second one. And then you just have to make sure that you're plugging it into the correct form for x2. All right, thank you for watching.